Hello students. Welcome to your school YouTube channel. Today's topic is, why do quantum effects only happen on the atomic scale? So without wasting time, let's quickly start the video and learn. Quantum mechanics is the science of the very small. It governs how particles like electrons, photons and atoms behave in the quantum world. Particles can exist into places at once, tunnel through barriers and instantly affect each other across distances. But these strange behaviors called quantum effects don't seem to happen in the world we experience every day. Why is that? The answer lies in scale and interaction with the environment. What are quantum effects? Quantum effects are behaviors that defy classical logic. They include superposition. A quantum particle can exist in multiple states at once. For example, an electron can be into different energy levels simultaneously until it's measured. Entanglement. Two particles can become connected so that the state of one instantly affects the other, even if they are miles apart. Wave-particle duality. Particles such as electrons and photons behave like both particles and waves. These phenomena have been proven in experiments and are at the heart of technologies like quantum computing, lasers, and atomic clocks. Why don't we see these effects in everyday life? If quantum mechanics is the foundation of all matter, why don't we see quantum behaviors in large objects like humans, trees, or buildings? The key reason is decoherence. The role of decoherence. Decoherence is the process by which a quantum system loses its quantum behavior and starts to act classically. It happens when a quantum system interacts with its surrounding environment. Imagine an electron in a superposition, existing into states at once. If it's perfectly isolated, it can maintain that state. But the moment it interacts with something, even a single photon or molecule of air, its quantum state collapses into one definite outcome. In the real world, large objects are made up of an astronomical number of particles. These particles are constantly interacting with each other and the environment, bouncing off air molecules, radiating heat, absorbing light. All of these interactions cause rapid decoherence. The result? The quantum weirdness disappears, and the object behaves according to classical physics. Scale and probability. At the atomic level, quantum effects dominate. But as you move up to larger scales, molecules, cells, or entire objects, the probabilities that govern quantum behavior get averaged out. You end up with predictable, stable outcomes. That's why a baseball doesn't go through a wall via quantum tunneling. Even though it's technically possible, the chances are so incredibly small, it's effectively impossible. This transition from quantum to classical behavior is not a mystery, it's a result of statistical laws. Larger systems are essentially built from trillions of quantum particles, and their combined behavior averages out to classical laws like Newton's laws of motion. Can quantum effects be seen in big things? Interestingly, scientists have managed to create conditions where quantum behavior is visible in larger objects. For example, in a Bose-Einstein condensate, thousands of atoms act as a single quantum entity. But creating this requires near absolute zero temperatures of isolation from all environmental noise. Quantum computers also rely on maintaining quantum states in larger systems, but only within ultra-cooled, shielded environments to prevent decoherence. Conclusion. Quantum effects only happen on the atomic scale because that's where particles are isolated enough to follow the rules of quantum mechanics. As systems become larger and interact more with their environments, quantum behavior rapidly vanishes due to decoherence. While the quantum world forms the foundation of reality, it stays hidden beneath the surface of our classical, everyday experience.